welcome back to the video. Today we're going to be looking at one of my most requested videos ever, the Lambert W function. And this is in honor of 1,000 subscribers, so I really thank all of you guys for subscribing and showing support throughout the community, and I hope we can keep growing, and it's truly remarkable that we've gotten here. Let's get right into the video. Okay, the Lambert W function is a very nice function that helps us in a variety of scenarios and has many applications in a lot of places. But let's take a look at what it actually means. So, if I have the function x times e to the x, just like this, not e to the x, but I just multiplied by x. If I wanted to solve for x, let's say that this is equal to 3, how could I solve for x in this scenario? You could try algebraic manipulation, saying x is equal to 3 times e to the negative x, or you could try taking ln. You could do ln of x plus ln of e to the x, cancel equals 3. Then you get ln x plus x equals 3. But you can't really get anywhere with this. You'll never be able to truly solve for x purely algebraically, which is why a guy named Lambert decided to create a function that's really handy, and it's called the Lambert W function. It's super handy because it allows us to apply it in this scenario on both sides, and it's defined as the inverse of x times e to the x. Now, what this means is it's going to output x. If w of, so if I have g of x is equal to x times e to the x, that means g inverse of x is equal to w of x. Now remember, this -1 does not mean 1 over g of x. It's a very common beginner mistake, but that's not what it means. It means inverse. Now with this new knowledge, we can expand and move forward. Let's put this to the side. Now this means, using the basic properties of inverse functions, we could say that w of x times e to the x equals x. But that also means that w of x times e to the w of x should return x. Because when two functions are inverses, we could say f of g of x is equal to g of f of x, which is equal to x, where f of x is equal to g inverse of x, just like that. So this holds true because we're plugging in our function w of x within our bigger function of x times e to the x, and it should output x both times, and it does, which means that these two functions are inverses. Now let's take a look where the w function, or the Lambert W function, even comes from in the first place. Let's begin by graphing our function that's really carrying this entire thing, which is x times e to the x. X times e to the x. Let's make a graph. Just like that. So you're going to see that this line is going to continue on for infinity. It's going to be asymptotically approaching 0, this line right here. Then there's going to be a dip. It's going to hit some value, and then it's going to keep going up and up and up and up and up, like that. Now, what is this dip equal to? It turns out this dip, the x value, is at -1, and we could calculate the corresponding y value by plugging it back into the equation. That means that x times e to the x will return -1 times e to the -1, which is equal to -1 over e, which means this y value right here is going to be -1 over e. Now, stay with me here. What happens if I cut this entire function into two pieces, left and right? And to understand why I just did that, you have to go back to the main function that this entire conversation is revolving around, e to the x. I'm sure all of you know the function e to the x looks like this, just like that, and a growing exponential that it's 1 right here, and it keeps going up and up and up. Now, to find the inverse of the function e to the x, which I'm sure all of you know, which is ln of x, what you do is graphically, this is true for all inverse functions, you simply reflect it over the line y is equal to x, just like this. Just like that. You reflect, you do all of it properly, you reflect over this line, you're going to get something that looks like this. Just like that. It's going to be asymptotically approaching the same way that this is asymptotically approaching. Now this function, as I'm sure all of you can identify now, is just ln of x. That is indeed our inverse function, and it's that simple. And this property holds true with literally anything. If you're working with lines or parabola, anything, the inverse is simply reflecting that graph over the line y is equal to x. And this holds true with the Lambert W function. Now, when we were talking about our function x times e to the x, when we graphed it out, we noticed something. Our graph looks like this, with the minimum point right here. What happens when we reflect this over the line y is equal to x? When we do so, we're going to get something like this. We're going to get something like that. We're going to get something that's asymptotically approaching the same way this is asymptotically approaching. And that minimum is kind of replaced with the minimum of x instead, and then it continues. But here's the issue. If I remove our actual function and just leave the Lambert W function now, which is the inverse, because we said this is x, the orange function was x times e to the x, and the inverse we said was w, f of x equals this. We could say f inverse of x is equal to w of x. So this is indeed the graph of the Lambert W function, but using the vertical line test, we could see that this is not a function, because for a singular input right here, wherever it is, it has two outputs, here and here, which makes it not a function. And we learned this in algebra too, because if we have any graph that's like this, we know that we represent this using two different graphs, or I'm sure this is some parabola using y is equal to plus or minus square root of yada, yada, yada. We don't say that y is equal to one thing and that's it. No, it's two functions, because this is not a function. It's failing the vertical line test because of two intersection points. Now, with this new knowledge, what did the folks who made the Lambert W function decide to do? Are they just going to stop the Lambert W function right here and not care about everything here? Of course not. They instead did what I did up here just now. I said we're going to cut this function into two parts, here and here, and we're going to call them branches. Now, if I take this new knowledge and move down here, by reflecting that function with that function x times e to the x over the over the line y equals x, and considering that little line which we drew to split the function into two, that line translates right here. Oops. The line translates right here. This means that our cut, or our new branches, are emerging at this point specifically. That means that this entire thing, let me do this in orange, is a different function than this. These are two separate branches, as we're going to call it. So, ladies and gentlemen, that leads me to my definition, that this is going to be w0 of x. This is the first and most principal branch of the Lambert W function. This is called the principal branch. And it is defined for values. The domain is going to be x is greater than equal to, what is this point? Well, I'm sure many of you know this, but we said that the domain, what's the domain of x times e to the x? For this onwards, we're not going to consider the left side because we split it into two functions. The domain, starting from that line which we drew, is going to be x is greater than equal to -1. And what's our range from that point? It dips to -1 over e. So y is going to be greater than or equal to -1 over e, just like that. When considering the inverse function, all that happens to the domain and range is they switch, which means the domain of the Lambert W principal branch is x is greater than equal to -1 over e, and y is greater than equal to -1. Now let's take this, and we're going to move it down there, because we can simply swap the domain and range, and it gives us the correct values for the inverse function. Simply algebra. If I move it down here, we now have a domain and range for this part of the graph. Now, what does this mean that this part of the graph is? They both intersect at the same point right here. And what is that point? Well, think about it. That point is going to be -1 over e, comma -1, based on our domain and range, which we just defined. That means that this part, or we're going to define that branch, by the way, as w -1 of x. So hence that branch there. And we're going to talk about that in just a second. We're going to define the domain of that to be x is greater than -1 over e, not greater than or equal to, greater than, and y is going to be less than -1. You can actually say this is inclusive because that point does exist as part of the branch. We're not too nitpicky about that. So x is greater than equal to -1 over e, but all the values are going to be less than or equal to -1 because we're including that now. But yeah, that's a little talk about our domains and everything. If you're considering both of these branches at the same time, then we can say the overarching domain of this is going to be x is greater than or equal to -1 over e, and y, well, this goes down to -infinity, and this goes up to infinity. What does that mean? Y is going to be from -infinity to infinity. And I'll write this as set notation. We're going to say that this is going to be equal to just -1 over e to infinity. So that's if we're including both of these branches like this. But where do we stop? Now, it turns out the branches which I just discussed, w of -1 of x, which you saw graphically, was this one down here, and w0 of x, which is this thing that goes up and up and up like that from that point, w and w0 of x, these branches are enough to cover all of the real numbers. However, you might notice something. Because we said that we could deal with our real values and this suffices, what if I'm trying to solve for this problem? Given our Lambert W function like this, like that, what if I'm trying to find w of -2? This is a real number, of course, and what did I mean by that? I meant that this function will output all real numbers, because this continues down and this goes up and up and up for infinity. However, when you're dealing with something like this is outside of the range of both branches that we discussed. However, the Lambert W function doesn't stop there, because it is defined and it does output certain complex values as well. It's multi-valued and it gives some complex values as a result. Now, when we were defining the principal branch of the Lambert W function of W0, what we actually did is we created a branch cut from the value of -infinity to -1/e, non-inclusive. That means that all of these values were essentially cut from our domain because we were trying to simplify this and create it to be actually usable. It's hard to give an exact definition of branch cut, but essentially all these values are still, you can still plug them into the Lambert W function and any branch, which I'm going to talk about, but it'll output a complex number. For x within -infinity to -1/e, the Lambert W function will return complex values. The Lambert W function will be within the complex set. The inputs lie on the real axis, but they fall outside the domain where any branch of w of x returns a real value, because the real values are w of 0 and w of -1. So hence, if you want to find w of -2, you can do that, but it'll equal some random 0.05 whatever plus something 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 I. It'll be some complex value like that. So that, I hope that makes sense. Now, using the properties we learned earlier, we can say that w of z times e to the w of z, where z is some complex number, should return us z, because this is just our algebraic properties. But this holds true if and only if w of z is technically equal to wk of z, such that k is an integer. That means if we lie on any branch, not w of 0, not w of -1, w of anything, it can be whatever number we want, any branch we want in the complex world, then this will hold true. And that's kind of a given because we can't really disobey this rule, really. It's hard to do that. I don't even know what w of 0.5 of z would be. That doesn't quite make sense because we're defining branches, but it's an interesting concept. But that's what that means. So any branches, the complex plane is supported. Now, something to note is the Lambert W function cannot be expressed in terms of elementary functions. It's useful in a variety of applications, but that means we can't express it as using basic functions that we know of ln or our trig functions. We can't use some function of those to describe it. It's one of our non-elementary functions. And similar to that, you'll notice, I could do a separate video on this, but when you're taking the indefinite integral of things like the Gaussian integral, the integral of e to the -x squared, this returns us the error function, just like this. The error function is another non-elementary function, and I could give a whole lecture about that too. But if you're familiar with that, then you can relate to that and know how, and understand how that doesn't really make sense to describe something that can't be elementarily solved. Now, I did this in my other video, but because this is a overall overview of the Lambert W function, let's quickly take the derivative of the Lambert W. We know that w of x times e to the w of x returns us x. Let's differentiate on both sides of using dx. dx. Now, on the left-hand side, we can use our product rule. We could get that w prime of x times e to the w of x plus w of x times the derivative of e to the w of x, which is e to the w of x, times w prime of x is equal to 1, because ddx of 1 is just 1. Oh, sorry, ddx of x is just 1. Then we can factor out our w prime of x times e to the w of x plus w of x times e to the w of x equals 1, because we just factor this out. Now, you'll notice that this entire thing, what did we just say that was? We said that this is equal to x by definition. So we can say w of x times e to the w of x, that's just x. So we can say w prime of x times e to the w of x plus x is equal to 1. And ladies and gentlemen, that means w prime of x is equal to 1 over e to the w of x plus x. Pretty nice. You can check out my other video for more explanations if that's not making sense. Now we can solve for the integral of w of x, just like this. The integral of wx, this is a little more tricky, but let's give it a shot. We can use u substitution. Let u equal w of x. That means we can solve for x using this. We just use our basic rules of Lambert W. X is equal to u times e to the u, because if this is w of x, then that should return us x by the inverse properties. Thus, if we get dx, that's going to be u times e to the u, using the power rule, plus e to the u times 1 du, just like that. Now we can substitute this back into our integral. We have integral of u times e to the u times u plus 1, just by factoring out, like that, du, like this. Now we're just going to multiply these two together, and what do we get? We get integral of u squared plus u times e to the u du, like that. Now we can use integration by parts. We're going to let this equal dv, and we're going to let this equal u, and you'll see why. Remember, our formula is equal to, of integration by parts is integral of u dv equals uv minus integral of v du. So we have u squared plus u. What is integral of e to the u? It's just e to the u minus integral of what is v, e to the u, and then du is just going to be 2u plus 1 du. And once you do this again, what's going to happen? You're going to get this, for the sake of time, I'll just write it out. You're going to get u squared plus u times e to the u minus 2u plus 1 e to the u plus 2e to the u. And simplifying things, you're going to get u times u, e to the u, minus ue to the u, because we're just going to flip it, plus e to the u. That's a lot of back and forth. And the reason I wrote it like this is because u times e to the u is just x. That's what we have. U, once again, is going to be w of x. And then we have this is going to be minus x, like this. And then we have e to the w of x. So ladies and gentlemen, that means the integral of Lambert w of x is going to equal x Lambert w of x minus x plus e to the w of x plus c. Now, lastly, to close off, I will just mention a few special values of the function, of the Lambert W function. These are on the Wikipedia page as well. You guys can check that out. I'm not going to be proving them, but just handy things to know. Lambert W on the principal branch of negative pi over 2 is I pi over 2, believe it or not. Lambert W, and this one should make sense because we discussed the domain, of negative 1 over e is equal to negative 1. And there's some other pretty cool ones as well. I encourage you to check them out. Something else to note is that the Lambert W function is commonly referred to as the product log because we use log on e to the x, and we multiply by x. It's kind of like product on something we use log on, hence product log. And you can enter it in Wolfram Alpha like this. And also, it's referred to as the omega function by my friends as well. So there's many names for it, and it's a pretty cool function. Lastly, for those who have stuck this far in the video, I will give you a bonus representation of the Lambert W function, which is as such. For the principal branch, truly astounding. I have not verified this. Other people have, and it's astonishing. The principal branch of the Lambert W function is represented as negative 2 over pi times the integral from 0 to pi of sine of 3 over 2t minus or plus xe to the cosine of t sine of 5 over 2t minus sine t all over 1 plus 2xe to the cosine t cosine of t minus sine of t plus x squared e to the 2 cosine of t all times sine of 1/2 t dt for absolute value of x, or just x in this case, is, or actually absolute value of x is less than 1 over e. Once again, we said that the Lambert W function cannot be described using any elementary functions. This is an integral, which means that this is not elementary functions. I don't believe this is not integrable. It does not look like it. Doesn't look like it will be. So this is not, this is indeed not any elementary function. So it's not not violating any property. The Lambert W function is used in a variety of fields in mechanical engineering, neuroimaging. It's used in even cryptography, I believe, but in creating semiconductors. Everything uses, many things use the Lambert W function. Very handy function. I hope you guys enjoyed today's video. If you have any questions, if I made any mistake, if you have anything to say, please leave it in the comment section down below. I really appreciate it. Wish you guys the best. Thank you. Drop a follow and like. See you guys.